We are at the fourth recording, at the beginning of the fourth recording of the structural mechanics lesson. The structural mechanics lesson has a total of 6 recordings, each about lasting about an hour. So please use that time frame to plan ahead for your study schedule. So we are in the concept of combined stresses. A given structural element may encounter both axial and flexural loads. Their normal stresses due to axial and bending forces can be added together, as shown in equation 44.42 of CERN and 44.43 of CERN. Shear stresses are a different type of stress and cannot be directly added. The interaction of shear and normal stresses is outside of the scope of the breadth portion of the exam. Bending stresses can be due to loads applied perpendicular to the axis of the member, as we saw in the previous concepts, or due to axial loads not applied directly over the centroid of the beam. The distance from the centroid to the point load is known as eccentricity. And you can see this in equation 44.43. So you have concentric and eccentric loading. So eccentric loading, that occurs when the load is not applied through the centroid of the beam. An axial member loaded eccentrically will bend, and it creates bending stress of the member. So here you can see how an eccentric load in figure 44.14 will bend a beam. And you can see here, let's zoom in into this location where the force is being applied, that the force is not being applied on the centroid of the beam. It's being applied at an offset from the centroid of the beam. That offset is what is known as the eccentricity. Eccentric loading, of course, will be different from concentric loading and axial loading. In concentric loading, load is applied to the centroid of a tension or compression member's cross-section. If an axial member is loaded eccentrically, it will bend, and it will experience bending stress in the same manner as a beam does. Since the member experiences both axial, and bending stresses, it is known as a beam column, such as the one shown in figure 44.14, where E is known as the eccentricity. The bending stresses in a beam column may cause a compression member to go into tension on one face. This can be avoided by keeping the eccentricity within the kern of the member. It is particularly important to eliminate or severely limit tensile stresses in unreinforced concrete and masonry piers, since these materials cannot support tension. Piers are designed as beam columns. So let's go through an example problem to put this to the test. The cantilever frame shown is supported by a 5 by 5 meters footing. So here is the cantilever frame. It has a force applied 10 kilonewtons at the top. It has a force of 5 kilonewtons being applied at the middle of the frame. Then it has a horizontal force of 15 kilonewtons being applied at the middle of its, let's say, lowest column. So most nearly, what is the maximum normal tensile stress below the footing? Is it 1 kilonewtons per square meters, 2 kilonewtons per square meters, 3 kilonewtons per square meters, or 4 kilonewtons per square meters? If you would like to go ahead and solve this problem using the concepts and equations that we have reviewed so far through the structural mechanics lesson, Please go ahead and pause the video at this moment. Now, one thing to highlight on this problem is that it's a theoretical case, as typically you do not see tension appear under the footing in most type of soils. So let's go through the solution. Normal stress occurs as a combined effect of both normal force and bending moment. So the normal force and bending moment at the foundation level must be calculated first, neglecting the thickness of the footing and the self-weight of the footing, and taking compression as positive. So we can find that the normal stress will be the sum of the forces acting on the footing. And we see that we have two forces acting on the footing. We have 10 kilonewtons and 5 kilonewtons. 10 and 5. So we have 15 kilonewtons of compression acting on the footing. Of course, we're not considering the weight of the frame. We're not considering the weight of the footing. Then we find the moments on the footing. So the moments that are acting on the footing are simply the sum of the forces times their moment arm that is acting on the footing, that is trying to overturn that footing. So we have 10 kilonewtons times 3 meters. 10 kilonewtons times 3 meters, just pointing down, plus 15 kilonewtons times 2.5 meters, plus 15 kilonewtons times 2.5 meters, just going in this direction. And then we have 5 kilonewtons times 3 meters. 5 kilonewtons times 3 meters, just going in this direction. You can see how this is going in the opposite direction. So therefore, 5 kilonewtons, because it's going in the opposite direction, is going to have a negative sign. So moments at the footing are 52.5 kilonewtons per meter. Now we have our normal and our moment force. So we need to then find our sum of our stresses. So for normal force, we need to divide the normal force over the area. So it's 15 kilonewtons over 5 meters times 5 meters. Because our footing is 5 meters by 5 meters. Note how there's no information on the footing down here. So this could be one of those problems where you have some information on the prompt and some information on the figure. And of course, you have key critical information on the prompt. So when you're solving for this type of problem, you may miss where's information on the footing, and you may make a wrong assumption if you do not realize that the footing information is given only in the prompt. There's another way that NCS can test to see if you have a good grasp of the overall problem. So that will give us our normal stress acting on the footing. Now for moment stress, it's going to be plus or minus, whether we are in compression or if we are in tension. So we have 52.5 kilonewtons per meter. Then we need to find the inertia of our rectangular shape, which is the base times the height to the cube over 12, times where our y component is. So we can get that our normal stress is between 3.12 kilonewtons per square meter when it's in compression and 1.92 kilonewtons per square meter when it is in tension. So the answer is B. What is the maximum normal tensile stress? Tension stress below the footing. 1.92 kilonewtons per square meter when it's in tension. So the answer is B. Note that here again on the question it's asking for a specific type of stress, not compression, but tensile stress. This example is commonly repeated in the design of footings. A quick check in this type of problem is to divide the moment by the actual load and calculate the eccentricity. This can be checked to see if it is within the middle third or the current point of the footing. If it is, then the tensile stress of the footing is going to be less than half over m over n. Let's start going into concrete properties. Concrete. What is concrete? Concrete is a mixture of cementitious materials, aggregates, water, and air. Sometimes you'll see that people will use concrete and cement as a synonym, whether in reality cement is a portion of concrete. Because concrete also has cement, aggregates, water, and air. Reinforced concrete is a term that we use when we have steel bars that are reinforcing the concrete or meshes that are reinforcing the concrete. However, concrete by itself does not mean that it needs to have any kind of steel component into it. Concrete by itself is just a mixture of cement, aggregate, water, and air. Now, concrete is relatively strong in compression and it's weak in tension. This is why we add steel bars to reinforce concrete, because we're reinforcing its weakness in tension. Now, concrete is an economical material choice for many structural applications. Now, if we look at table 48.1 within CERN, we'll see different volumetric proportions for concrete ingredients. Now, values in this table are approximate and average, so they provide you like a quick check on the values for the volumetric proportion of concrete. The behavior and design of concrete is driven by the fact that concrete can carry compressive loads and must be reinforced in order to carry tensile loadings, and we reinforce concrete with steel. One reason that concrete is an economical choice is that the primary volume of concrete is made up of aggregates that can be sourced virtually anywhere in the world. Here we see table 48.1 from CERN, which shows the typical volumetric proportions of concrete ingredients. We can see two divisions on concrete. We have air-entrained and non-air-entrained concrete. And we have the different components. We have coarse aggregate, fine aggregate, water, Portland cement, and air. Coarse aggregate can be considered the gravel that's used in concrete, while fine aggregate is typically considered the sand that is used in concrete. Then we have the water content, the Portland cement, and the air content. Now, these are just kind of like cut check type of volumetric proportions. Now, you may have a problem in the exam that you may need to define or find the water content in a concrete, or the volume of coarse aggregate in concrete, or the mass of coarse aggregate in concrete using some kind of volumetric proportions given in the problem prompt. So that's another way that the exam can test you on if you know how to determine the volumetric or the mass proportions of concrete ingredients. Now, cementitious materials. Cement paste is a mixture of Portland cement and water that binds. It acts as the binding agent for coarse and fine aggregates, and it binds into a rock-like mass. Cement powder comes in 5 types, each with their own advantages. Pozzolanic additives such as fly ash can add strength and durability to concrete. Cement has a specific weight of approximately 195 pounds mass per cubic feet. Note how cement's specific weight is higher than that of typical soils, which is 120 pounds mass per cubic feet. Cement is packaged in standard sacks or bags, which weigh about 94 pounds mass or 40 kilograms. Cement paste hardens during the chemical reaction of water and cement, which is known as hydration. During this process, the chemical reaction between the water and cement will release a lot of heat. ASTM C150 details the 5 classifications of Portland cement. And you can also see this in section 48.2 within CERN. We have type 1 cement, which is normal Portland cement, general purpose cement, and it's the most used of your type 1 cement, and is used when no sulfate hazard is expected. Type 2 cement, it's modified Portland cement, and it has moderate sulfate resistance. Type 1 and 2 cement is often used because it meets the requirement of type 1 and type 2 cement. Type 3 cement is a high early strength Portland cement, and it develops strength quickly. Now, you can see why type 3 will be used in some applications. When you need the strength of the slab or the strength of the concrete element to be developed quickly so that you can continue or perhaps accelerate a construction schedule. Type 4 cement is a low heat Portland cement, and is typically used for massive concrete structures, such as gravity dams. And type 5 cement is sulfate-resistant Portland cement. It is used when you have exposure to sulfate concentration. And the next key component within concrete is aggregate. And aggregate makes up about 60 to 75% of the total concrete volume, which is the reason why concrete makes concrete an economical type of material. It consists of fine and coarse aggregates. It consists of sand and gravel. And aggregate properties will influence the behavior of freshly mixed concrete and the properties of the hardened concrete. Aggregates must be strong, clean, hard, and free of absorbed chemicals. Fine aggregate consists of natural sand or smaller crushed stone. Fine aggregates must meet particle size requirements, must meet grading requirements. So you can see how in the exam you may be tested in both topics, into the proportions of concrete and into a gradation requirement to see if you can read a gradation table and then determine what is the proportion that's needed of that specific fine aggregate for the specified concrete mixture. Coarse aggregates consist of natural gravel or crushed rock. Individual pieces are large enough to be retained by a number 4 sieve. A number 4 sieve has an opening size of 2/10 of an inch or 4 3/4 of a millimeter. Now you can see how coarse aggregate, the number 4 sieve, becomes your division between gravel and sand. Coarse aggregate has 3 main functions in concrete. It's a relatively inexpensive filler, it resists the applied loads, and it reduces the volume changes that occur during setting. Now we get into the last components of concrete, which are water and air. There's also an additional component of concrete, which are admixtures to modify some of the chemical reactions that occur within the concrete to make the concrete fit a specific purpose. So what does water do? Water hydrates the cement powder and begins the chemical process, which affects the concrete strength and its workability. Air is added to the concrete to increase its durability. Admixtures are used to modify various properties of the concrete, such as the concrete working time, the concrete settling time, the concrete slope, and many, many others. Now, there's additional, what I like to call cosmetic additives that you can add to concrete to perhaps have it give it a specific color tint or give it a specific roughness finish. 1 ton, 2,000 pounds mass of water has a volume of 240 gallons. Water used in concrete should be potable in order to conform to ASTM C 1602 and have no pronounced odor or taste. And the reason that ASTM C 1602 calls for potable water to be used in concrete is to make sure that the water does not have any additional chemicals or additional minerals that may interact negatively with the concrete chemical reaction. With some quality restrictions, the American Concrete Institute, which is known as ACI, allows for non-potable water to be used in concrete mixing. Impurities in water may affect the setting time, the strength, and the corrosion resistance of concrete. Admixtures modify the performance of concrete. Some of the advantages of these admixtures include creating concrete that has a higher strength, a higher durability, a higher chemical resistance, and a higher workability, a controlled rate of hydration, and for reduced shrinkage and cracking. Accelerating and retarding mixtures fall into several different categories, classified by ASTM C494. Water-reducing admixtures disperse the cement particles throughout the plastic concrete, reducing water requirements by 5 to 10%. Now, I've been mentioning codes from ACI and ASTM. You do not need to have these codes handy or know the standards by heart for the breadth portion of the exam. I'm just mentioning them to, give you some grounding, give you some bearings on the specific standards that govern our design for concrete mixtures. Now, you will not need to refer to those to solve any problems during the breadth portion of the PE exam. Concrete compressive strength. The concrete compressive strength is known as F prime C. Maximum stress a concrete specimen can sustain in compressive axial loading. That is the compressive strength that's been called out in concrete mixtures, is the maximum stress a concrete specimen can sustain in compressive axial loading. So the concrete compressive strength is typically determined by casting concrete cylinders and then putting those cylinders into a press and determining the force that's needed until those cylinders are crushed. Typical values for the concrete compressive strength range from 3,000 psi, pounds force per square inch, to 6,000 psi, pounds force per square inch. And one key factor that you will find is that the concrete compressive strength will increase as the concrete cures. That's why you have additives or concrete or cement types that are called high early mixtures. And the reason why is that will allow you to have a compressive strength quicker or faster in time. Now, as part of my professional experience, I worked in a geotechnical, in a testing laboratory. So we did quite a bit of tests. And one of the tests that we did the most was that of the concrete compressive strength. And one of the things that is typically can be done during construction is, if you test your concrete and let's say you have a specification of 4,000 psi, pounds force per square inch, that you need to meet on your concrete, that typically it's interpreting construction that is the strength that the concrete needs to meet before I can put any additional loads into it, or before I can sell that, I've reached my spec on my concrete and I can move to my next construction task. So what can be done sometimes during construction projects to accelerate your schedule, because you need to wait about 14 days for concrete to reach their design strength, is that The concrete compressive strength can be tested earlier than those 14 days, perhaps 7 days, or 5 days, or 6 days. So the cylinders can be crushed earlier, and that determines like if the concrete strength specified strength has been met. So if we crush cylinders, let's say before the 14 days, 7 days, and the compressive strength was met 4,000 psi or greater, then the contractor will have the green light to move on to the next construction task. Now, the compressive strength may also be reading as CXX, such as C20, C30, C40, and that's in SI units, where XS is the compressive strength in million pascals, which is equivalent to newtons over millimeter square. And this is also commonly used. Typically, the concrete delivered at the construction site will be stronger than the design concrete strength. And the reason why is because the concrete supplier is also being a little bit conservative to make sure that he meets his specifications. So he'd rather err in the side of being cautious than having to, rip apart an entire foundation because it didn't meet the specified concrete strength. F prime C is determined by testing concrete cylinders. Typically, the design strength of the concrete is specified at 28 days. However, cylinders are often tested at 3, 7, or 14 days. Now, a typical 7-day concrete break strength is about 70% of the 28-day break strength. While the concrete strength may increase with time, the increase in strength levels off at approximately 28 days. So you can see that the strength versus time curve will flatten out after your first month. So here we see the typical concrete compressive strength characteristics based on the water-cement ratio and the strength of the concrete given in PSI. The concrete compressive strength is controlled by the water-cement ratio, the coarse and fine aggregates, and the admixture. Here we see a chart that relates the compressive strength with the water-cement ratio. Well, I kind of deleted there the legend for the y-axis. The y-axis is the concrete compressive strength measured in PSI. Now, you can see that there are two curves drawn here. So this is also giving you an additional relationship between air-entrained concrete and non-air-entrained concrete and their water-cement ratio and what the compressive strength will be yield for that specific concrete mix design. Provided that the mix is of a workable consistency, the strength varies directly with the water-cement ratio. This is also known as Abraham's strength law. The water-cement ratio may be stated as the number of gallons of water per each sack of cement, which each sack is about 94 pounds force. And the typical values are between 5 to 7 gallons of water per sack. A mix is often described by the number of sacks of cement needed to produce 1 cubic yard of concrete. For example, a mix using 6 sacks of cement per cubic yard will be described as a 6-sack mix. Now, the water to cement ratio is something that NCS loves to test in the P exam. So more than likely, you will find one problem that requires you to determine what that water to cement ratio is. And NCS may ask you to determine that ratio between gallons per sack, or perhaps a 6-sack mix, or perhaps in just volume percentages, mass percentages, many different iterations. But the key is that you understand how you determine that water to cement ratio. Now, concrete workability. What is workability? Workability is the effort required to 1. Transport, 2. Place, and 3. Finish wet concrete without segregating the aggregates or without bleeding the concrete. And bleeding means just squishing or, well, yes, I guess I'll use my technical term, squishing the water out. In its wet state, concrete has a good workability, and workability is often closely correlated with the slope test. And the slope of a concrete is simply you put concrete on a cone, inverted down, almost like a pyramidal cone, right? You put concrete in that pyramidal cone, you remove this pyramidal cone, and then you measure how much the concrete sloped from its shape. And that's how you can measure the workability of the concrete. So if the concrete is stiff, it will retain the shape of the cone. If the concrete is malleable, it will not retain the full shape of the cone. If the concrete is extremely wet, it will just have no shape of the cone. So you can see the two extremes. If the concrete is too dry, it's hard to work because it's almost like you're just moving rocks around. If you're moving just sticky rocks around. If the concrete is too wet, it's hard to work because it's almost like you're just pushing water around. You wanted the concrete to be somewhere in the middle of those two extremes. Low workability concrete may result in honeycomb concrete, which is weaker and has lower durability. Table 49.1 of CERN gives typical slumps by the application of concrete. Typically, a structural concrete requires a slump between 1 inch and 4 inches. Self-consolidating concretes can have very high slumps. In these concretes, an alternative spread test is performed. The test measures the diameter of the slump concrete instead of its change in height. So what is the slump test, right? Let me do a quick sketch to highlight what the slump test is. So the slump test, we have a cone, a pyramidal cone. That's an opening at the top. So concrete is poured on the top of the cone. That as that concrete starts to settle on the cone, you bring it all the way up. So that concrete starts to fill in the cone. Now, if we remove the cone, the concrete is filled up to this point, right? And you stir with a bar just to kind of get the concrete to evenly distribute through the cone. So once you have stirred with a bar the concrete to make it uniformly distribute through the cone, you lift up the cone and you may find that the concrete will have a slump shape. So let's say our concrete shape right now is something like this inside the cone. That's our concrete shape inside the cone. So we remove the cone, we will see that the concrete will slump and we'll have a shape perhaps like this. And I should probably use a different color. We'll have a slump. We'll have a shape that's somewhere like that, right? And the slope is measured from the top of that cylinder. So it'll be that dimension that will be measured in the slump. And that is correlated to workability. So you want the concrete to slump a bit because you want it to be malleable. You don't want it to be stiff, but you don't want the concrete to slump all the way to the bottom to just be so watery that it's difficult to work with. So that is the overall concept of the slump test. Now for durability. Durability is the ability of concrete to resist environmental exposure or surface loadings. One of the most destructive environmental factors is the freeze-thaw cycle. ASTM C666, which is the standard test method for resistance of concrete to rapid freezing and thawing, is the standard laboratory procedure for determining the freeze-thaw durability of hardened concrete. This test determines a durability factor, the number of freeze-thaw cycles required to produce a certain amount of deterioration. This freeze-thaw cycle is bad for concrete because as water gets into the concrete and freezes, it expands. The expansion of the freezing water causes internal tensions in the concrete, and as we know, concrete does not handle tension well, which in turn will cause cracking and spalling of the concrete. And because concrete does not handle tension well, so we have, let's see, we're talking about concrete and reinforced concrete. So first, if we have our concrete to start cracking and spalling because of tension on the freeze-thaw cycle, that cracking and spalling will carry out to defects into the compression strength of the concrete, which is what the concrete is being used for its compressive strength. So that will then impact the compressive strength, and then will create more cracking and more spalling until that concrete will fail. Now, for reinforced concrete, we have added a reinforcement to handle tension better. But however, if there is not enough reinforcement to handle the freeze-thaw cycle, we can still see some cracking and spalling. Now, that cracking and spalling can allow for moisture to get into the steel bars. Therefore, those steel bars will then start to corrode. And when those steel bars start to corrode, they start losing their tension stress capability, their ability to withstand tension. So then we go into this vicious cycle. We start losing more tension, concrete starts to crack and spall more, then we get to a point where that cracking and spalling is starting to impact the compression strength of the concrete, and then at the end we'll have this even reinforced concrete can fail. Now for concrete strength, the American Concrete Institute, which is known as ACI, under their specification 301, details the acceptance of concrete testing. Concrete strength is a function of the water-cement ratio. It's inversely proportional to strength, and the water-cement ratio has to be typically between 0.4 and 0.6. Cylinder sizes of either 4 inch by 8 inches or 6 inch by 12 inches are permitted, which are the ones that are used to collect the samples of concrete. Smaller cylinders are used when the compression machine has a lower capacity. Single strength tests could be performed at times other than 28 days, but the tests are specified as 28-day tests. For concrete strength acceptance, a single strength test is the arithmetic average of concrete compressive strength of at least 2 6 inch by 12 inch cylinders, or at least 3 4 by 8 inch cylinders. Single strength tests are generally performed at 28 days. The concrete strength, or the specified concrete strength, is known as the F prime C. This is what ACI 301 under 4.23 dictates that the compressive strength of concrete is satisfactory if no single strength test is 500 pounds force per square feet less than the design compressive strength of the test for concrete that's less than 5,000 pounds per square feet, or 5,000 pounds per square inch, or no single strength test is 10% less than the design test for concrete that has a greater strength of 5,000 psi. And the average of every 3 consecutive strength tests equals or exceeds the specified compressive strength. If any of these criteria is not met, then the concrete is considered unacceptable. Now, you do not need to know this criteria from ACI 301 for the breadth portion of the exam. However, the reason I'm going through this is just to give you an idea on what the parameters are for the strength of concrete. And now we're starting to get into concrete mix design. Here we're going to cover the absolute volume method. It determines yield when mixing known quantities of ingredients, and it uses densities of all ingredients to calculate the absolute volume each occupies in a unit volume of concrete. So let me zoom in so you can take a look at equation 49.1 of CERN. So this is the absolute volume. So you have the mass over the specific gravity times the density of water. On US units, you have the weight over the specific gravity times the specific weight of water. Now, to use the absolute volume method, it is necessary to know the solid densities of the constituents. In the absence of other information, you can use table 49.2, which is shown in CERN. Now, the values in the table are approximate and should be used only if other information is not available. Now, for the NCS P exam, because the values for the different constituents for different types of concretes will vary from, let's say, material pit from material pit or from supplier to supplier, use table 49.2 more as a gut check to see if you're on the right track. Because NCS, because of that variability on the material properties, NCS will more than likely have to provide you those values or provide you a way to calculate those values in the exam. Because of that variability, we enter into the realm of subjectivity, which can be used to contest a problem in the P exam. So that's why NCS typically will not require you to look up these values, especially if they vary from supplier to supplier. Yield is the volume of wet concrete produced in a batch, and is typically measured in units of cubic yards. The unit weight of an ingredient is the specific gravity of the ingredient multiplied by the unit weight of water. Here we see table 49.2 of CERN, which provides us with a summary of approximate properties of concrete components. See, even the title of this table is kind of giving you caution. Do not use this to solve a PXL problem. This is a summary of approximate properties. So it is not giving you, this is not a standard. This is not a given. This is not a constant. This is just an overall summary of ranges of approximate properties, just to give you some bearing, some benchmarking when you're working for problems in the P exam, and to also help illustrate the theory. So we have cement, we have the specific weight of cement, the specific gravity, and the weight of one sack. We have fine aggregate, the specific weight, the specific gravity, coarse aggregate, specific weight, specific gravity, water, specific weight, measured in many different units, and a specific gravity. Now, for water, I will say on this table, for water, you can use the values given on this table to solve for problems in the P exam. Because the specific weight of water is like a common standard. Now, coarse aggregate and fine aggregate will vary depending on the supplier. But water is going to be the same anywhere that it gets used. So it's given as a standard. Now, what I really like about this table and why I'm going to recommend that you tab this table is because this is one of the few spots in the CERN book that you get the specific weight of water in different units. And the units that are being used here are those units that will help you solve volumetric concrete mix design type of problems. So that's why I will recommend that you tab this table. And you may want to perhaps use a highlighter or to simply box this part out. And it is because of these different units that you're being provided on this specific weight of water that will help you solve many different problems when it comes to volume mix type of problems of concrete mix design. So now back to our main lesson. Concrete curing. The hydration of cement is what dictates the time a concrete will cure, and it affects the strength that concrete achieves. temperature and humidity must be controlled. So concrete should be saturated or nearly saturated until hydration is completed. This is why you see to maintain that saturation, you will see that sometimes concrete slabs get covered with wet burlap to make sure the concrete stays saturated. Now, the loss of water causes the concrete to shrink and crack. Concrete strength will increase with age as long as moisture and favorable temperatures are present for hydration of the cement. The three primary methods of keeping concrete moist and at a favorable temperature are described in section 49.12 of CERN. So if you'd like to read a little bit more on these different type of methods, please refer to section 49.12 of CERN. Now we're going to go into some of the material testing specifications as given by ASTM. Now this is not that you will need to look up these values in some specific ASTM standard, but more to give you the theory that guides the design of concrete mix design. Now for the compressive strength, ASTM C39 gives you the information for a compressive test specimen mold cylinder and concrete cure for a specific amount of time at a specific temperature. And it tells you that the specimen has to be actually loaded to failure at a specific rate. And this is given by equation 48.1.